Hi everyone, welcome to another video in this series going through some past exam questions on redox titrations. This is the third of 4 videos looking at iodine thiosulfate redox titrations. And this question is slightly different to the ones we've seen before. Both of the questions we've seen in previous videos have been about something to do with copper. We can see, which is the most common thing that comes up with these questions. But we can see we've got something involving chromium this time, so that's exciting. Question's still the same though. Massive wall of text, massive blank space, 6-mark question. So that hasn't changed. We're going to approach it the same way. I'm not going to bother reading all of that until we have to. Let's find the question. We are going to read all of that, just to be clear, but not to start with. Right, in step 1, what we've got, sodium oxide and sodium ion, whatever it is thing, weird, react with water to form an alkaline solution containing a brown precipitate. This is not a redox reaction, okay. Write equations for the reaction of sodium oxide with water. Okay, so we've got to do this separately. All right. So Na2O reacting with water. And then in the second one, we're going to have this NaFeO2 reacting with water. Okay. So what's going on here then? Let's just go and have a look at step 1. What's it saying here? Just see if there's anything more important looking at here. Chromite ore is heated with sodium peroxide. Fine. We've got an equation there. Water is added to the mixture. Okay. This dissolves. Okay, none of that's really relevant, is it? Okay. Right, so what's happening here then? If these two react together, well, if sodium ends up in water, it's going to make sodium hydroxide, right? And this explains why it's making an alkaline solution. It's going to make sodium hydroxide. This, I would imagine, is also going to make sodium hydroxide. Okay, and if it's making a brown precipitate, that's going to be the iron reacting. Let's just check the oxidation numbers here. So it's saying it's not a redox reaction. I mean, sodium's not going to be oxidized or reduced, is it? It's always +1. But the iron here, so if sodium's +1, the oxygen here is -2, isn't it? -2 minus 2 is -4. So if that's +1, the iron must be +3. So we're going to end up, if it's not a redox reaction, then we're still going to end up with iron in oxidation state +3 here. That's important. And that's why it's a brown precipitate. If you've done the transition metals part, yeah, you'll know that iron 3+ gives you a brown colour. Iron 2+ is a greeny kind of colour. And so if this is going to make a precipitate, this is going to be a precipitate of iron hydroxide. And if we've just worked out, it's got to stay at the same oxidation number, so this must be FeOH3. Right, so let's just balance this then here. I've got 2 sodiums, so that's balanced, right? 2 sodiums, 2 oxygens, 2 hydrogens. That looks fine. Here I've got 1 sodium, so that's done. I've got 1 iron. I got 3. What have I got? 4. 3 oxygens plus 1 is 4, and 3 hydrogens. So I've got 4 oxygens and 4 hydrogens. So I've got 2 oxygens there. So if I put a 2 here, that should work out. 2 oxygens, 2 oxygens. Gives me 4 and 4 hydrogens. Okay. I think we're done with that. Right. What's this bigger question? It wants us to determine the percentage biomass of chromium in the ore. Okay. So this is very simple. We had a question with percentage of copper in a piece of brass in one of the previous videos. So it's going to be similar, but obviously we've got a different reaction. Again, I'm going to approach this exactly the same way. I'm going to go through this massive chunk of text and find all the numbers that I'm going to have to use. Got a volume there. We've got a concentration here. That's just a ratio. We've got a 25 centimeter cube sample. We had 1 decimeter. Oh, look, they're really throwing the boat out here and making this different. This isn't 25 to 250. It's 25 to 1 decimeter cubed. So that's going to change things as well. This is exciting, this question. And we've got a mass. Right, where are we going to start? We're going to start at the bottom and we're going to work our way up. Yeah, like we usually do. And the first part is going to be the same. We're going to calculate the moles of thiosulfate, and then we're going to use the ratio. So we're going to start with these two numbers. So it's 25.5 over 1,000 times by 0.1. Where are we? Here we go. So 25.5 over 1,000 decimeters cubed times by 0.1. That's going to give me moles. And hopefully you can see, if you've watched more than one of these videos, hopefully you can see that I'm literally doing the same method every time. Right? It will work. I'm laying it out almost exactly the same every time. We're putting the units on. We're making sure we know what it is that we're calculating at every point. That is the moles of the thiosulfate. And then once we've worked out the thiosulfate, we're going to look at the ratio in the equation compared to the iodine. So the ratio of the iodine to the thiosulfate, you probably know this by now if you've seen this before. It's a 1:2 ratio. So it's 1:2 this way. So therefore, we need to divide by 2. Let's take this, let's divide it by 2. 1.275. That is now the moles of iodine. Okay. Right, we now know about the moles of iodine. Where did the iodine come from? That's come from here. So we can now go from the iodine to the chromium, because they've told us the ratio here, it's 1 to 1.5. So similarly to what we did before, you do the ratio and then you do the ratio again. So now the ratio of this, what was it, CrO4? Yeah, 2 minus. CrO4 2 minus to iodine, said was 1 to 1.5. Have I got that the right way around? Yes. So if that's the number of moles of iodine that we've got here, to get the moles of the chromium, we're going to need to divide by 1.5. Okay. So at least we're not just timesing by 2 and going back to the same number like we've done in the other questions. So it is a bit different. So we're going to do this 1.275 times 10 to the minus 3 divide by 1.5, didn't we? So we're going to take this and we're going to divide by 1.5. So we've got 8.5 times 10 to the minus 4 moles of the CrO4 2 minus. Okay. Okay. So where are we here? So now we've got the chromium. We've done that. So now we're going to have to do the scaling up bit. So that's in 25 centimeters cubed. We need to scale this up to 1 decimeter cubed. So normally this is 250 we've seen before, so you times by 10 to make it 250 centimeters cubed, and then we times by 4. So we're going to have to times by 40 to go from here to here. Okay. So that is the moles in 25 centimeters cubed. So 8.5 times 10 to the minus 4 times 40 is going to give us 0.034. Okay, so 0.034 moles of this chromium in the 1 decimeter cubed. Okay. Right, where are we? We're here. So now we're going to end up using the mass. What are we trying to calculate? We're trying to calculate the percentage by mass of chromium. Okay. So if this here is the number of moles of CrO4 2 minus, that's also going to be the number of moles of chromium. Because there's just one chromium atom in every ion. So we can just multiply this by the relative atomic mass of chromium. Okay. So we're going to say 0.034 moles times by, where's chromium? Chromium's atomic mass here is 52. So we're going to times it by that. Let's work that out. So 0.034 times 52 gives us 1.768 grams of chromium. Right, and then we want to do this as a percentage. So hopefully this is smaller than the mass we had at the start. Ooh, yeah. 5.25 grams, okay, it's not even close. So we want to do 1 point divided by this one, don't we? So we're going to do this 1.768 divided by 5.25 and then times it by 100. So let's work that out. Divided by 5.25 times by 100. 33.6. Well, what was it saying? 1 decimal place. Okay, so it's 33.7%. Okay, so very similar kind of method. It's just obviously a bit of a different question with the chromium ions rather than with copper that we've kind of got used to with the other two questions. Okay, right, there's an extra little bonus bit here just for fun. So this part refers to step 2 of the method. Right, let's just have a quick peek at step 2. So the mixture is filtered and it's made up to 1 decimeter cubed. Sample is pipetted in a conical flask and potassium iodide is added. Redox reaction takes place. Okay, so it's this reaction. They gave us the ratio of. Okay, that's going to be useful, isn't it? They presumably want us to write this equation, right? In this reaction, these ions are reduced to chromium 3. I minus is oxidized. Construct an overall equation for the redox reaction and write half equations. That's a weird way of writing it, isn't it? We're going to do the half equations first, right? We're going to do the half equations and then use those to build up the equation. It's a bit of an odd way of doing it. Okay, so we've got 1 half equation is involving this chromium. That's being reduced to Cr3+. So let's look at the oxidation numbers here. So this is obviously +3. Here the oxygen is -2. -2, -2, -2, so that's -8. And it needs to add up to 2 minus, so the chromium here must be +6. Let me just make sure I've got a space here for the second half equation. Right, so if chromium's going from +6 to +3, then it's being reduced, like it says, so that's good. If it's reduction, it's gaining electrons, so we're going to add the electrons here. And if it's +6 to +3, it must be 3 electrons, right? So now we just need to finish this half equation off. We've got all these oxygens that we need to balance. So we've got 4 oxygens, so I'm going to have to put +4 H2O here. And then I've added in 8 hydrogens, so I'm going to put +8 H pluses over here. Okay, am I allowed to do that? Does it say anything about being in alkaline conditions or anything? Yes, it does. So it's always worth checking that. Looking at the mark scheme here, they will let you get away with doing it with H+ ions. But in this case, we need to be using the hydroxide ions. So that's a bit annoying. Right. So what we want to do here then is, this is kind of awkward because what you want to do here is do this backwards then. And actually it tells us, so what I was going to say is, if it was in acidic conditions, we'd put water here and we'd put H+ ions here. Okay, but we know it's in alkaline conditions, so actually what you kind of do is just shift both of those one-way alkaline. So instead of having water here, you'd have OH- ions here, and you'd have to have the H2O where the H+ was, because that's the more acidic one out of the two. But actually it tells us that anyway. Look, it says it's a reaction between I-, CrO4, 2-, and H2O. So this is going to have to be on the other side. So we're going to have some number of H2Os on this side of the equation. So this is just going to be a pain in the backside for balancing though, isn't it? Right. So let's just do this. It's going to take us a while. But if I've got 4 oxygens here, so let's put 4 OH- in here. So that's balanced the oxygens. And then I've got 4 hydrogens there. So I'm going to have to put 2 H2Os to get my 4 hydrogens. Okay. But now I've got 6 oxygens here, haven't I? 4 + 2. So this now needs to be a 6. But now I've got 6 hydrogens. So this now needs to be a 3. But now I've got 4 plus, I've got 7 oxygens now. So that needs to be a 7, except it's never going to be a 7 because I need to have an even number of hydrogens. So let's make this an 8. So I've got 8 hydrogens, so that now needs to be a 4. This is where a piece of scrap paper comes in handy for you to do it beforehand, before you end up ruining your exam paper. 8 hydrogens, 8 hydrogens, 8 oxygens, 4 and 4. So there we go. That's done. Let's just check the charges balance. That's always a good thing to do. I've got 2 minus plus 3 minus. That's 5 minus on that side. I've got 3 plus and 8 minus. I've got 5 minus there as well. That's fine. Right, so that's one half equation. The other half equation is I minus oxidized to iodine. At least that's nice and easy. I minus is going to I2. It's got to be 2 of those. It's going to lose 2 electrons, right? Okay, so that's not too bad. Right, now we want to combine these together to make the overall equation. We're going to need to make these electrons balance out, aren't we? So we're going to have to times this one by 2, and we're going to have to times that one by 3 to make it work. So let's go for this then. We're going to have 2 of this thing. The electrons are going to cancel, plus 8 H2O, plus, we've times this by 3 now, so that's going to be 6 I minus. It's going to make 3 I2. And the electrons are going to cancel. And here I've times this by 2, so I've got 2 Cr3 plus. And times that by 2, so it's going to be 16 OH minuses. Let's just check that the charges balance here. Make sure we haven't messed anything up. 2 lots of 2 minus is 4 minus. It's off the screen. 4 minus here plus 6 minus. That's 10 minus on that side. And I've got 16 minuses, but I've got 6 pluses. Okay, so I've got 10 minus on that side as well. So there we go. Okay.